Welcome back to another lesson in pre-calculus. This is Mr. Bean. Today we're going to study some things called inverse trig functions. This picture here is something to get you real excited for the end of the lesson because I know you're already excited for the end of the lesson, and you'll see. I'll explain this when we get to the end there. So inverse trig functions. Let's first remind you how inverses work with some operations you are already familiar with. This first one, x plus 5 equals 13. What are you going to do to both sides? Real simple. Subtract 5. You get x equals 8. Here, what do we do to both sides? Divide by 7 to both sides, and we're going to get 5. Now, why are we dividing by 7? Because this is multiplication, and the inverse of multiplication is division. Same here, real simple. Inverse of addition is subtraction. Here we have an exponential function, and so how do we get rid of an exponent? We take the logarithm of both sides, so we're going to get log base 2 of 24. And then the last one, this is something that Mr. Brust covered a little bit with us in our previous unit, and that is you take the trig inverse, or the sine inverse of both sides, in order to get our variable, theta, all by itself. So theta will equal sine inverse, with this little negative 1 up here, of 1. Okay, today's lesson we're going to focus a little bit more on this stuff, dealing with the trig inverse functions. So to begin, you got to know some notation. Arc sine is exactly the same thing as inverse sine. In other words, if you said sine inverse or inverse sine, and you were saying something like this, like of the angle, sine inverse theta or inverse sine, that is identical to just saying arc sine. So whenever you see this, you're going to see both in our notes and our lesson today. So just keep that in mind. It means the same thing. First of all, we're going to see how to graph this stuff. Now, I'm really hoping this is going to make sense because I think I've got it figured out how to make this as easy as possible. So this is our original sine graph. Remember, it goes through the origin. So I'm going to write down one of the coordinate points, 0, 0. Another coordinate point, if I come over here to, let's go to pi over 2, this point right here. So that is a coordinate point of pi over 2, 1. Let's keep going. I've also got the coordinate point pi, 0. And then this coordinate point here on the valley, that would be 3 pi over 2, negative 1. And then we'd get back here to one more coordinate point, which would be 2 pi, 0. Okay, so now we have some points. So what I want to do is, if we're doing the inverse, if you remember inverse functions, that's where you take the x value and the y value and you swap them. They trade places. So to get over to the inverse function, we're going to swap them. All right, so here's how we do that. Well, the 0, 0, that's easy enough. It's still just 0, 0. This one's going to be 1, pi over 2. This one will become, this one here, you switch them, it becomes 0, pi. And then this one is negative 1, 3 pi over 2, and then the last one I have written down would be a 0, 2 pi. Okay, let's plot those. So we have 0, 0. What else do we have? We have 0 pi. I have this one of 1 and pi over 2. I have this one, negative 1, 3 pi over 2. And then I have the 0, 2 pi again. So what's going to be happening on these graphs is the inverse is going to take this wave and it actually flips it around, and it does something kind of cool like this, where it's doing the wave along the y-axis. So if you'll notice, what I did to help you is I put the scale of the y-axis in terms of pi and the scale of the x-axis in terms of just units 1, 2, 3. So now if we were graphing this thing, this is where you really need to be using a pencil. So if you don't have a pencil, don't copy this whole thing down, what I'm about to do. I'm going to have this thing curve. It would continue here. So we're going to curve like so. Okay, that's supposed to be a nice curved sine graph. So there's our inverse sine graph. But this is not a function, because it fails the vertical line test. See, it crosses all over the place there, so it's not a function. So what we do is, to make it become a function, we have to restrict our domain and range. And the way we think about this for sine is we're always going to be here in quadrant 1 for all of these inverse functions. So we're going to be using quadrant 1. For sine, that's positive values. Where is sine also negative? Sine is going to be negative down here in quadrant 3 and in quadrant 4. That's where sine is negative. But it wouldn't make sense to use quadrant 3 and 1 because they're not even close to each other here like to make it a continuous function. So we're going to use these angles right here, the angles that go from negative sine to positive sine. So this is from negative pi over 2 up till we get to pi over 2. Okay, so this is what we're using. For the sine graph, you got to really think about this. For sine graph, this would be the domain. The angle is the domain. But for the inverse of sine, it is the range. So that's why down here I have listed from negative pi over 2 to pi over 2 because it is the range. So that means we're only looking at, let's grab the eraser, we're only looking at, for the range values, negative pi over 2, which is right here. That's where it starts. That's the bottom of it. So anything below that we get rid of. And then the top of it is going to be pi over 2. So where's our pi over 2? Right here is pi over 2. Okay, so that is the only part of the graph that we look at. Let's fix this graph. I don't like the way the thing looks because that looks like a straight line, and it is not a straight line. So it should be curved because that would be a, whoops, it would be a nice curved graph like that. Okay, so try to make it obvious that the graph is curving, right coming to these 2 points. What is the domain? The domain is the old range, the range of sine. So the bottom here is a negative 1, the top is a 1. And if you flip the range of the sine graph, negative 1 to 1, then that becomes the domain. So we go from negative 1 to 1. And that's our graph. Okay, so now what are we going to do with this thing? It's just this weird little thing for sine. Remember, it goes through the origin. All you're doing is when we have some special things for our shifting, like let's say it was, I don't know, something like 3 sine inverse of some value c. We'll talk about this c in a little bit. It's just some variable, input variable. Then that means you take all of the y values and you multiply them by 3. So this pi over 2 would become 3 pi over 2, and it gets vertically stretched, exactly like we've done all year this year and in Algebra 2 and all that stuff. You just vertically stretch it by a factor of 3. And same with any type of shifting or rotation, so you'll have that in your practice. Let's go to the arc cosine, or cosine inverse. Before we stop plotting a bunch of points to see what it looks like, let's think about this first. What's the domain of this graph? Well, the domain is all real numbers. It goes on forever and ever and ever. But what we had talked about was just focusing in on quadrant 1, because that's where cosine is going to be positive. And then where is cosine also negative? Here in quadrant 2. So those are the 2 quadrants we'll look at for cosine and then cosine's inverse. So let's review that again. Sine inverse, it's positive in quadrant 1, and then down here in quadrant 4 is where it's negative. So 1 quadrant of negative, 1 quadrant of positive. Then we go to the arc cosine, 1 quadrant of positive and also 1 quadrant of negative. So you have to remember that this is the angle 0 and the angle of pi. That is the domain of cosine. In other words, the input values. But when we go to the inverse, that's the output values. Angles are the output of cosine inverse, so therefore it goes from 0 to pi for the range. So the lowest it's going to be is at 0, and the highest it's going to be is at pi. So now we'll see where those graphs go. I'm going to pop up here just a list of coordinate points from this thing. Okay, here's some points, and I only went from 0, pi over 2, and pi because I saw the range of the inverse is from only 0 to pi. So if the range of the inverse is 0 to pi, then I only wanted to worry about the domain of 0 to pi on the cosine. I know. Oh yeah, this sounds confusing, huh? Okay, so 1, 0, let's plot that point. 1, 0, 0 pi over 2, and then negative 1 pi. So it's not just a straight line. Remember, this would be like a wave that would be going back and forth on the y-axis, but we restrict that domain and range, and so let's curve this, and then I'll erase part of it so we can kind of better have a nicer graph. So let's get rid of that part and then get rid of that part. There we go. There is the graph of the cosine inverse. Okay, so remember that the sine inverse will go through the origin. Let's go back and look at that one. Sine inverse goes through the origin, and it goes here left to right. And then the cosine inverse graph will go shifted up pi over 2 units. So it's going to start right there, and it's going to start here left to right and go down. This is one of these things you've got to memorize if you can't reconstruct this in your head. If you're able to reconstruct it with these coordinate points and you can remember what the domain is, then you can always get this graph correct. Just remember you got to have some translations and reflections and all that type of stuff. Last graph, and that is the tangent inverse. Let's list some points on this thing. Let's see here. I've got 0, 0. So that's an easy one. When I flip the coordinate points there, it's still going to be 0, 0. How about, where's another one? Well, I'm going to have a vertical asymptote, right? Let's draw the vertical asymptote. I'm going to have a vertical asymptote at pi over 2 and at negative pi over 2. So let's put that case on this one. We're going to have horizontal asymptotes at negative pi over 2 and another horizontal asymptote at pi over 2. Then we're not going to keep going. We're just going to sketch this one thing right here, and this is what the tangent inverse graph looks like. It's going to go off like that, approach that horizontal asymptote, and go off here to the left. And that is our graph for tangent inverse. We would not keep doing this over and over again up and down here because that would fail the vertical line test. So you're not going to have a whole bunch of lines like this one. It's just this one with horizontal asymptotes. So what's the domain of the inverse? Well, if the range here is everything, then the domain on the inverse is everything. What is the range of arctangent? Here we have cutoffs on the range. It's just wherever the horizontal asymptotes are. So we're going to be using quadrant 1 because tangent is positive there. And then for this one, we come down here and we go from negative pi up to pi. So that may not make much sense to you, but hopefully this graph does. The graph might make more sense if we're taking this one and you just kind of flip it over and you get it on the side for the horizontal asymptotes. Okay, there's our two graphs. Again, you might be stretching this up and down depending on what other numbers we plug in for this thing. Next up is looking at the angle compared to looking at the two sides of a triangle. Now, this is one of those things that kids mess up quite a bit, so let's focus. Thinking caps on. Here we go. This right here is the angle. Okay, so angle is this part of it. That theta is the angle, which means what is it going to equal? Well, from our basic trig, right triangle trig, we know that sine theta is equal to opposite over hypotenuse. So katoa. So this is the angle, and this is two different sides of a right triangle. That's what we get for our normal thing. So what does the inverse do? The inverse would be we're going to switch these things around. We're taking the inverse of the two sides of the right triangle, and it is going to equal the angle. So when you have a trig inverse function, the answer is the angle, and what's inside are the two sides of the triangle. So if you need to write that down, make sure you get that down very, very clearly. Here you have the angle with a regular sign, and when you have an inverse function with trig inverse, the answer is the angle, and the inside represents the two sides of the triangle. Let's do that with cosecant. So when we have cosecant, if you think through that, well, cosecant is just the reciprocal of sine. And let's see, the reciprocal of sine then is going to be hypotenuse divided by opposite. Now then that leads us to cosecant inverse. If we're doing the cosecant inverse, well, remember how the outside is the angle, right? If it's a trig inverse function, the outside's the angle, so in here goes the two sides of the triangle, which would then be hypotenuse over opposite. So that then is going to equal this. Now why am I switching to sine? Why make it so confusing? Because your calculator does not have a cosecant inverse button. There's no way to plug that button in on the calculator, so we need this. Sine inverse is the reciprocal of cosecant inverse, but remember, you only take the reciprocal of the two sides of the triangle. That's what you take a reciprocal of. You don't do a reciprocal of the angle. It's the two sides of the triangle, and then that will then, of course, equal the angle. Okay, so you may need to rewind and listen to that again. That's a very important explanation if you did not understand this. I'm going to show you how to do this with a calculator now. So our first step here for number 1, we have here cosecant inverse of 2.67, and we want to figure out what that equals. So let's use this example up here. This 2.67 represents the hypotenuse over the opposite. So I don't have a way to plug this in a calculator because my calculator does not have a cosecant inverse. So what I can do is say sine inverse of, and then I'm going to change it to 1 over 2.67. Now that's what I can plug in to my calculator. 1 over 2.67. So let me grab my calculator, pull this up here, and we'll say, the mode. Let's go to degrees on your mode. I'll explain this in just a minute. So degrees, you could do radians or degrees, but I'll explain why I'm choosing degrees here just momentarily. And go back, quit. So sine inverse, there's my sine inverse. So second, sine inverse, 1 divided by 2.67. Close the parentheses, enter. And I get 21.995, so pretty much 22 degrees, because that was what my mode was. So the answer to this is, I'm going to switch to red here, get a little bit more room, 22 degrees. So how do I know if the answer was in degrees or radians? You have to go with what the instructions tell you. I had no instructions for this one, so there was no way for you to know if the answer was radians or degrees. So just look at the instructions and to see if your answer was in radians or degrees. Also, as a reminder, what did I flip here? I didn't flip the whole thing. I didn't make this 1 over sine inverse. I only flip the ratio. Okay, the ratio of the two triangles. I only flipped the ratio that represented the two sides of the triangle. So the 2.67 was the hypotenuse over opposite, and I flipped it. Okay, here, secant, 0.15. Now, think through this. Where is our angle? In this case, our angle is right there. This is the angle because it's not an inverse. That is important to identify every single one of these problems before you plug it in a calculator. Identify where your angle is, because that's what you know what you're going to flip. So then this is going to equal the same thing as the 1 over, what's the reciprocal of secant? Cosine? Cosine of 0.15. Close parentheses. Now, how do I know if I'm using degrees or radians? In this example, it's not based off of the instructions. It's based off of what the angle is. And the angle, 0.15, there's no degree symbol, so it must be radians. See, over here, this was not an angle, so we didn't know if it was radians or degrees. You got to follow the instructions to say what the answer should be. But in this case, this is the angle, and it says right there, there's no symbol, so it's got to be radians. That is an important thing to understand in order to get these problems right. So we just plug in, oh wait, got to change it to radians since there's no degree symbol. And then we say 1 divided by cosine of 0.15. Close my parentheses, and we get 1.011. 1.011. All right, that is how you do this stuff with plugging in a calculator. Next up, how in the world are we going to solve something like this without a calculator? All right, it's not too bad. We're going to first take what Mr. Bruss taught us, and that is when we have a sine inverse, so we have square root of 3 over 2, and we're not being allowed to use a calculator. So, hold on, I'm ignoring this tangent right now, okay? I'm going to bring that back here in just a minute. But if we're not allowed to use a calculator, then we know that a sine inverse is going to equal an angle. So you have to think about our unit circle or the chart that you filled out, those things that we want you to memorize and know when does the sine of an angle, so sine of what angle equals square root of 3 over 2. Sine of what angle is going to give us square root of 3 over 2? Remember, this is the two sides of the triangle. Well, remember that on our unit circle, we're going to have quadrants 1 and quadrants 2, in which we'll have a positive sine value, because this is a positive square root of 3 over 2. But we only care about this being the domain of sine inverse. Look at the top of your notes at the beginning here when we talked about what we deal with, and we're only caring about these two quadrants. So we get to ignore this one right here. We completely ignore quadrant 2, and we only focus on quadrant 1 values for where we get the sine value of square root of 3 over 2. And when is that going to happen? That's going to happen at either 60 degrees, or if we wanted to say radians, you could say pi over 3. This is the same thing, 60 degrees or pi over 3. I guess technically I should probably have something like a y equals to say that this is a function, because when we're dealing with functions, we're only going to have this restriction for a sine inverse, or the arcsine. Okay, let's get rid of this. We don't need that to finish this off. And we'll go back here and say I've got the tangent of, so arc sine of square root of 3 over 2, what angle is that? That is going to be 60 degrees, or pi over 3 if you prefer to use the radians. And then the tangent is going to be sine over cosine. What is sine over cosine? Well, sine of 60 is going to be, oh, I gotta move this down, give myself a little bit more room. So that's going to be the square root of 3 over 2. And then the cosine of 60, because tangent is sine over cosine, the cosine is going to be 1/2. And I just know that because I've done these 100 times, and so I'm fairly fast at them. This is what I love about tangent. Whenever you have tangent and have these halves over halves, it's like the halves cancel. So all you have left is square root of 3 over 1. So the final answer is the square root of 3, and there we go. Done with that one. Number 4. This one we're going to use a reference triangle. So let's make a nice, oh, that's a nice triangle, nice right triangle. And we're going to figure out sine inverse of 5 over 13. Well, if you remember that, right here, this whole thing is just an angle. It's like a big theta, sine inverse of the two sides of a triangle. So we're going to say, which one do we want to use? It doesn't really matter. I'm just going to go with this one. Say that is our angle theta. And sine represents opposite over hypotenuse. So our opposite is a 5, and the hypotenuse is a 13. So what this is we have tangent of an angle. I do not know what the angle is. I could use a calculator to help me out, but that's going to give me a decimal answer, and I want to get exact for these. But I don't need to know what the angle is, because if I know that this just represents some angle theta, then all I really want is to know what tangent theta equals, and tangent is opposite divided by adjacent. So all we need is this side right here. What is that adjacent side? So you use Pythagorean theorem. You could do 5 squared plus b squared, I guess, equals 13 squared, and solve it, and you will get a 12. So it's a 5, 12, 13 triangle. Therefore, tangent of theta is opposite divided by adjacent, which in this case will be a 5 divided by 12. And that is it, 5/12. So you just, when you use a reference triangle, you have to set up your triangle, use your theta, and figure out what the two sides are, find the missing side, and done. And then the last thing, let's just do this word problem real quick. I wanted you to have a little bit of practice seeing me go through one of these, because you'll have this in your application as well. So we've got a photographer who's standing over here with his camera, and he's watching a balloon go up in the air. He's 500 feet from it, though, and he's just taking some pictures. Okay, he's a long ways away from it, but he's taking pictures of this balloon as it goes up. So we want to come up with, write an equation to model the angle of his camera as a function of, and this is the key here, as a function of the height s. What that means is, this is how you write that, theta as a function of s. So that means theta s equals, theta of s, I should say, equals, and now over here you're going to have some things with just some s's in it. Well, the first thing is, how do you measure this angle with an opposite side and adjacent side? You say tangent theta equals the opposite over adjacent. All right, so if we solve for theta, then you're going to get theta equals tangent inverse of s over 500. Okay, that there is our formula for theta. So now we're going to graph this thing. Let's see, so our input is s, the height. So this represents, whoops, this over here is going to represent s, or in other words, our height. And then the other one, this one is going to represent theta, or the angle of elevation. Okay, that's what this thing is. So the angle of elevation, as you go up and up and up and up and up, the largest at the angle of elevation, it's never actually going to get to 90. Okay, so the farthest up it could possibly be, let's think about that. Is that right? Yeah, because you're not ever going to, if you're just standing there, you're not ever going to look straight up in the air. It might seem like it's close to being straight up, but if it gets higher and higher and higher, you're not looking exactly straight above your head because you have this distance of 500 feet, if we assume the balloon goes straight up in the air. So this angle will grow bigger and bigger and bigger, but it's never going to get up to 90. So I think the top of this we could say is just 90 degrees. And then the height, well, that goes for a long ways. You could say the height's pretty far. So I don't know. Let's just be reasonable here. Let's say the farthest that this camera is going to say is, I'm just actually totally guessing. Let's just say 1,000 feet and see what it looks like. Grab my calculator. Let's go back to degrees instead of radians. We could have done either one, but let's just use degrees because I put degrees on my my chart over here. Plug this in. Close the parentheses. Enter. And then I said my window was going to go from, so my x value is the height, so we're going to start at 0 height, and we're going to go out to 1,000 feet in the air. And then my y values have to do with the angles, so I'm going to say the first angle is going to be 0 degrees if it's on the ground, and then it can't ever get to 90. So we'll say a maximum of 90 degrees. Graph it. Let's see what it looks like. Ooh. Okay, that seems about right what it's doing. So the angle is going to be slowing down. It's getting bigger and bigger, and then it's slowing down. So that then is my graph. And you can just do a quick little sketch. Something like this. All right, to end the lesson, here's a little video of this guy who's got these weird little pendulum swings, and each one has a different length, and therefore they swing at a different rate. And so the period of them, depending on the length of the pendulum, changes. And so they kind of do some cool synchronizing things here. There you can see for yourself. But this is the end of the lesson. Rock that mastery check, and good luck on your test for this unit. And hopefully I'll see you back later in the course.